Welcome to the Global Composite Expert webinar series. My name is Wenbin Yu. I'm the Director of the Composite Design Manufacturing Hub. I'm delighted to have you all join us today. This webinar series examines the history, present capabilities, and the future of composites. Our goal is to share the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. Our center is located in the Indiana Manufacturing Institute. We welcome all of you visit us and exploring the cutting-edge facilities and resources available at our center. At CDM Hub, our mission is to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. Our vision is for CDM Hub to become the premier resource for composite design and manufacturing. To achieve this mission and vision, we have developed a powerful website called cdmhub.org, which serves as a platform for the composite community to collaborate and innovate together. We invite you to join cdmhub.org and take advantage of the wealth of knowledge and resources available at our website. This webinar series is just one of the initiatives that the CDM Hub has launched to serve our community. This webinar series is made possible by the generous support of our sponsors, including Dassault Systems, Cytec Solvay, and Anna Swift. We extend our heartfelt gratitude to our sponsors and acknowledge their commitment to advancing the field of composites. We also welcome other organizations to join us in supporting the global composite community. Together, we'll create a bright future for our field. This webinar will be recorded and made available on cdmhub.org. We will email you once the recorded video is available online. The presentation is about 45 minutes, then followed by a Q&A section for 10 minutes. All the attendees are muted at portion. Please submit your questions through the Q&A box to be answered after the presentation. For the sake of time, your questions may be summarized and rephrased for the speaker to answer effectively. All your questions after the webinar will be sent verbatim to the speaker for answers at their discretion. Now, I would like to invite Professor Dianren Zhang to introduce our distinguished speaker today.
Welcome, everyone. I'm honored to introduce today's webinar speaker, Professor Greg Odegard. Professor Odegard is a John O. Hawkins Endowed Chair in Computational Mechanics in the Department of Mechanical Engineering, Engineering Mechanics at Michigan Technological University. He is the director of the NASA Institute for Ultra-Strong Composites by Computational Design, which is focused on the development of the next generation of composite materials for manned deep space missions. Before joining the faculty at Michigan Technological University, Dr. Odegard was a researcher at the NASA Langley Research Center from 2000 to 2004. He received his PhD at the University of Denver in 2000. His research is focused on computational modeling of advanced material systems. He is a recipient of the NASA Outstanding Public Leadership Medal, is a fellow of the American Society of Mechanical Engineers, and an associate fellow of American Institute of Aeronautics and Astronautics. Now I will give it to Professor Odegard.
Thank you very much for the very nice introduction. My name is Greg Odegard. It's an honor to be invited to give this webinar. I really appreciate the opportunity, and I hope that everybody gets to learn something really interesting. So Today, we're going to talk about USComp, what USComp is and what we do. I will get into that in the presentation. And essentially what I'm going to do, I'm going to talk about that, and then I'm going to show some examples of some of the work we've done in this institute and how it helps reach NASA objectives as well as fits into the Materials Genome Initiative. All right, so let's start from the beginning. Of course, with this type of webinar series, I don't really have to talk about what a composite material is, so I get to skip that part. But what I want to talk about today is what it takes to have composite materials that can get us to the next step when we're trying to go to deep space. As it turns out, we use composite materials in a lot of things. In aerospace, 787, some of the newer Airbus aircraft, high-performance sports cars, sporting good equipment, things like that. We have done a really good job of developing composite materials that fits those roles and meets those specific needs. At the same time, when it comes to deep space exploration, we've become very good at sending rovers to Mars, little robots that can pack up very nicely at the top of a rocket into a very tight, confined space. We could take that little robot to Mars, we could drop it off, it could do its thing, and it stays there and it never comes back. And that seems to work really well for rover missions. However, if we're really serious about sending people to Mars, the story changes quite a bit. People are inherently selfish. Apparently, they need things like water and food and space. You see on the screen right here some of the things that if we were to send people to Mars, if there were missions to achieve with those people on Mars, there's a lot of stuff that has to go along. You have habitats, vehicles, solar panels, gas storage, just a lot of, and food as well. A lot of different things that have to go along. These things all add tremendous amounts of mass, right? Much more mass than what we have to worry about when we send a little rover to Mars. So you can think about this, the more mass we have, the more fuel we're going to need to get that mass there. The more fuel we have, the bigger the rocket is. The bigger the rocket is, the more mass there is. The more mass there is, the more fuel is needed. So it is not a linear problem. In fact, several years ago, NASA did some calculations on this, and what they estimated using the rocket equation, if you're going to send people to Mars and all the corresponding mass that has to go with them, it's going to cost $1 million per pound of cargo in fuel in order to get there and back. In other words, if I'm going to Mars and I weigh 160 pounds, it's going to cost $160 million in fuel alone just to transport just my body there. And that doesn't count all the other things that go along with it. So you can see how these numbers increase pretty rapidly, a little bit more than what the average taxpayer wants to pay. So in addition to this, NASA also did some basic calculations, and then if we could do this affordably, all right? And we're going to get to that in a moment. But clearly, what it requires is new materials. All right, now, let's talk about materials development a little bit. Materials have been developed since the early days of mankind, right? Then, of course, we get into the 20th century, and a lot of that accelerated tremendously, both when it comes to developing engineering alloys and polymers and composite materials and ceramics. But if you take a look at the 20th century and maybe part of the early part of this century, most of that type of materials development was experimentally oriented. All right, so that means people would go in the lab, they would play around with different material formulations, they would make it, they would break it, and they'd go back for another iteration. Now, there's some major issues with this type of approach. It's relatively straightforward. It's algorithmically, it's not that difficult, right? But as you can see on the list here, there is some issues with it. So first of all, when you're developing something, even like a composite material, and doing the kind of characterization, there's high costs associated with that. The materials themselves are expensive, particularly the materials we're dealing with on this project. Very, very expensive materials. People are expensive. If you have a lot of people in the lab trying to develop the material, you're going to have high labor costs. Also, if you're focused on experimental work to try and develop a material, eventually you're going to have to test those materials under extreme conditions. All right, so for example, high strain rates, extreme temperatures, whether that be really hot or really cold. Those of you in the audience who do a lot of experimental work, these things are not easy to do. All right, very high temperatures, very low temperatures, high strain rates. you have to have a lot of specialized equipment. It takes a lot of money and a lot of time and a lot of effort to set up experiments to test under these conditions. All right. The third item that you see on the list here, although we have some great experimental tools that give us a lot of information, even some of the characterization tools, we don't necessarily know experimentally everything that we need to know of what's going on the molecular level. We have a lot of clues, a lot of hints, but there's a lot of details we don't necessarily know if we rely purely on experiments. And also on the experimental approach, it brings us down to more of a trial and error approach to do this, sort of an iterative method. We call this Edisonian method. And you probably all know his famous quote, "I have not failed, I've just found 10,000 ways that won't work." All right, so maybe in the 20th century, it was okay to try 10,000 ways when we're developing composite materials, but it'd be really nice if we could do something a little bit different. Now, fortunately for us, as we get into this age, into the 21st century, we've got really powerful computational modeling capability. All right, computational modeling changes the whole approach to developing new materials. So, for example, you see, I put some examples on this slide here. There's maybe a few of us in the audience that remember the computer in the lower left right there. I was learning how to use that in elementary school. And at the time, of course, that was the coolest thing. It was very powerful, right? But now we laugh at that, thinking about what we see, for example, in the lower right, where just last year, Frontier came online, fastest supercomputer in the world, 2 quintillion calculations per second. All right. So you can see in about 40 years, we have come a really long way in computational power. But how does that help us? Well, computational modeling can really help us accelerate material development. First of all, it can provide a really efficient means to explore design space. If we could parametrically adjust material design parameters, do it very quickly, use structure property relationships, we can very quickly understand what kind of material or processing parameters need to be adjusted in order to yield the optimal properties that we're looking for. All right. Also, computationally, we can predict material behavior under a very wide range of conditions. So I just said earlier, when you have really high temperatures or really low temperatures or really high strain rates, experimentally, it takes a lot of effort to be able to set up those experiments. Well, people like me who do computational simulation, I don't have to do that. I just change a number. That's it. I just change the temperature. I change the strain rate. That's all I have to do. No special equipment. So computationally, it really allows for those type of extreme behaviors. All right. And also, computationally, if our models are working correctly, we validated them, it could provide a tremendous amount of physical insight into observed behavior. For example, with materials, we can understand fracture modes a lot easier, or any kind of other behavior that we see the results of in characterization. We could go back into our model, look very closely at what's going on, and be able to explain the experimental observations that we're making. All right, now, before I get into the meat of this, there's another thing I want to talk about, and that's the Materials Genome Initiative, MGI. So this came out in the Barack Obama administration back in 2011. The idea behind this was that we needed to figure out a way to, much like the Genome Initiative in the earlier part of this century, we needed to figure out a way to cooperate worldwide in order to develop materials to meet the actual needs that we have. All right. Sometimes just us working alone in our silos, either at our individual offices or our universities, or even just in a silo in our own country, we really can't take advantage of all the resources around the world, all the expertise that we need. And so the Materials Genome Initiative is the thought that we could really work together, develop computational tools, brand new computational tools, brand new experimental tools, and also take those, have them open to the public, generate a tremendous amount of data, and be able to put that in a database or multiple databases. So having all this digital data together with these new tools can really accelerate material development. Now, the funny thing is, when this first came out, things like machine learning and artificial intelligence weren't really much in our vocabulary. So this was a perfect segue into this modern era where we really utilize machine learning and we need tremendous amounts of data. So the idea behind MGI is we can put all this together. We can solve all the world's problems you see on the outer periphery of the circle here: clean energy, national security, human welfare, and developing the next generation workforce. Now, putting this all together, NASA realized they had a problem when it comes with being able to afford fuel on these deep space missions, particularly the ones that have people on them. And so they came out, this was probably in about 2016, came out with a solicitation for what I'll explain here in a minute, Space Technology Research Institutes. They realized that in order to meet the goals, they had to quantify the requirements. And that's what you see here on the screen. First of all, if we want to be able to enable composites or any material for that example for deep space missions, we needed to be able to have a quasi-isotropic specific tensile strength that's basically triple of what we had before, 3 GPa per gram per cc. I know that number probably doesn't mean a whole lot because it's odd units, but basically that's strength per unit mass density, right? And these are essentially threefold increases over state-of-the-art composites. Also, a specific tensile modulus of 150 gigapascals per gram per cc. In addition to those tensile properties, they also recognize that having a 50% increase in fracture toughness, specifically interlaminar fracture toughness, would also help enable a new generation of composite materials for deep space missions. All right, the other thing is, of course, a lot of us can develop these types of materials in our laboratory. We can maybe make small samples of them, samples we can hold in our hand. We can publish really nice papers on them, but we can't necessarily build a rocket out of something we can just make, in handful quantities. So NASA also specified we need to be able to scale it up to panel level testing. So this basically brings it to the technical readiness level, or TRL level 3. All right, which goes beyond basic research, but starts to push it into more applied research. And also NASA realized that things like this sometimes are hard to do alone. If we used an MGI-based approach and we work together as a big team, utilizing all of our tools and our ability to share data, then we could rapidly accelerate how we develop this material. So this solicitation came out in 2016. It was for what's called Space Technology Research Institutes by the Space Technology Mission Directorate of NASA. So we applied our team and we were awarded one of the 2 first-generation NASA STRIs. So the total funding of this has been about $17 million over 7 years. This started in June of 2017. So if you're doing your math, you realize we're coming to an end right here. So it's kind of nice. I can kind of talk about this towards the end of the project and really highlight some of the achievements that we have. Pictures there from our meetings. You can see we have a good group of people, a relatively large group of people. In fact, total, if you take a look at over the whole 7 years, we have a total of 12 universities involved. All right, and I'm going to show you a list of those 12 universities. We've got a few materials manufacturers, which have been really critical. Us university people, we like to think we can do it all ourselves, right? But at the end of the day, when it comes to developing materials, unless we have materials manufacturing involved, not only supplying the materials, but giving us feedback as to what it's going to take to actually commercialize and manufacture material, we really can't make much progress. So we're really thankful to have some materials manufacturers involved. Of course, NASA was involved not only from an administrative standpoint, but also technically. We had got some great technical folks at NASA who have been deeply involved. Air Force Research Laboratory has been a partner, and also several aerospace companies, which you'll see a list of here shortly. So the 12 universities, I have them listed here, as well as the PIs from each of the universities. The front 4, the ones in blue right there, those are sort of the leadership universities. NASA had specified this in the solicitation that we needed these leadership universities. So Michigan Tech, Florida State, University of Utah, and MIT. But also we had a lot of help from University of Colorado, VCU, Florida A&M, Georgia Tech, Johns Hopkins, University of Minnesota, Penn State, and UMass Lowell. And by the way, so all the PIs are listed right there. I know you're probably trying to read those names real quickly, so hopefully I give you enough time to see all your colleagues there. And then I notice on the list of people that are here, several of these people are here. So also we had some really good industry and government lab participants. Of course, NASA Langley Research Center, as well to a certain extent as Glenn Research Center, really had a lot of input and a lot of really helped us out quite a bit. NASA Langley's also got some parallel projects, and when you have parallel projects, they really augment each other very nicely. And so, playing off of each other, we were able to synergize quite a bit and make a lot of progress. Air Force Research Lab has been involved. I want to thank David for his involvement. As far as the materials manufacturers, NanoComp. So NanoComp is, if it's not one of the world's largest manufacturers of nanotubes, it probably is the leader in manufacturing nanotubes up in New Hampshire. They're owned by Huntsman. So not only did we have the resources of NanoComp, but also of Huntsman, who supplied us a lot of resins for this work. Solvay was a very close partner. We work quite closely with a lot of their resins in order to make the composites that I'm going to talk about today. Northrop Grumman, they've been involved the whole time. They've ramped up their involvement here in the last couple of years. I'm not going to get too much into that because there's a lot of stuff we haven't published yet. But also Textum is a composites manufacturer. They're very closely involved in what we're trying to achieve. And Boeing and Lockheed Martin have also been along with us from the very beginning, given us their insight. All right, so I haven't yet talked about anything technical. What I want to do before we dive into the technical stuff is sort of give an overall impression of the Institute. So if you consider all those universities and labs and companies involved, if you think about all the professors and all the students, all the postdocs, all the staff members, it's a large team. I mean, I'd have to take a look at our numbers, but probably total number of people involved over the last 7 years, we're probably approaching 200 people. There's a lot of individual efforts. And so early on, what we realized is that in order to achieve what we wanted to achieve, we needed the tools, right? And we didn't have the tools. We had sort of the beginnings of tools, but we needed really to take those tools and develop them further in those first 3 years. So we took this large team and we chunked it off into 4 sub-teams: a simulation and design team, materials synthesis team, a materials manufacturing team, and a testing and characterization team. And it was the job of those teams to develop their respective tools, whether it be computational tools or experimental tools or manufacturing tools, to develop those so that once we can develop them and that technology was mature, then we could go to the next step. So after about 3 years, we began to realize that our tools were developed. And if we wanted to achieve those really stiff goals I showed you a few slides ago, we're going to really need to find a way to take those tools and put them to work. So what we did, transitioning between years 3 and 4, is that we reshuffled the whole team. So we kind of dismantled the tool development teams, and we now put together tool integration teams. So instead of very specific things like you see on the left, or I shouldn't say specific, very broad categories that you see on the left, we put together a series of teams. There's actually more than one I've listed, but I just have 3 examples listed here. We put together teams that took individuals who were simulation people, experimental people, manufacturing people, materials development people. We took them out of their silos on the left and we put them together into more applied teams on the right, so that when these teams are working together, we had people from all kinds of different expertises and backgrounds trying to do things very specific. For example, modeling-driven improvements in CNT composite materials. Also, we had a very large team looking at surface treatment, as well as fabrication and testing of carbon nanotube-based composite materials. We wrote a whole journal article on just this topic, this transition here. You can see the citation there is on the right-hand side. Interesting. If you want a copy of it, just let me know. I'm happy to provide that. Now, before I get into specifics of everything everybody did, I kind of want to I want to give you the results first, right? Because I think it helps give you a picture. If you can see the big picture first and what we achieved, then it kind of gives a little definition to the individual projects, which I'll talk about after this. So I plan to spend some time on this graph. There is a lot going on here, and I don't want you to feel rushed looking at it. So we're going to go through it piece by piece. You can see on this graph, we're plotting specific modulus, that is modulus per unit density, up on the vertical axis versus specific strength on the horizontal axis. Now, as you can imagine, ideally, we want a material that's in the very upper right region of this graph right here. I think you can see my laser pointer there. All right, that's where we want materials. Those are materials that are both stiff, strong, and lightweight at the same time. For us composites people who mostly deal with a lot of aerospace applications, this is the sweet spot up here. Now, if we go to the very opposite end of this graph, we've got the high-performance aluminum and titanium alloys. All right, these are really well-developed alloys. We've had decades and decades of development. We use them on commercial aircraft, experimental aircraft, military aircraft. Great materials, but even though we're talking about aluminum and titanium, in the world of metals, they're lightweight. In the big picture, they're not lightweight. You know, if you take a look at their properties, they fall in the very lower left-hand quadrant of this graph right here. Now, for most of us who really are highly involved in composite materials, we know we break away from that by offering materials that have almost the same type of stiffness and strength, but with a much lower weight. And so the next thing I want to point out on this graph are these gray swaths here where you see the black diamonds. These black diamonds represent traditional carbon fiber composites, state-of-the-art. For example, IM7. IM7 8552 is sort of the benchmark composite material, state-of-the-art composite material that we often compare things to right here. So that's the standard material. T1100G fibers using ag composites, that's like Boeing's, fiber of the future and their composites right here. So you can see these commonly used composite materials generally have a specific modulus that is above the alloys, and we're talking unidirectional properties here, but certainly with a higher specific strength. Now, there's also high modulus fibers as well. They may sacrifice a little bit on the strength, but they also contribute to a higher modulus, right? So that's these three black diamonds you see right here. Now, if you haven't picked up on this already, USComp, mainly what we're trying to do is use carbon nanotube type materials, which we'll go into more details here in a moment. We use those type of materials to try and break away from the traditional state-of-the-art composite type of design and do something very different and try and improve both the modulus and the strength. So if you take a look at this blue highlighted region right here, you see a couple data points. Most of these are supplied Cecil Evers. This publication right now, which just came out a few months ago. By using carbon nanotubes in a very specific way, which you'll see, we were able to get these blue data points right here. All right, you can see that these blue data points really almost double what we have with our state-of-the-art composites that are commonly used for aerospace applications. They also push the modulus beyond and the strength beyond what we typically have with high modulus composite materials. So with this type of technology we're talking about, we were able to really push it up. Following this up, a journal article that just came out 1 or 2 months ago here from J.G. Park and Associates down at FSU, we used gamma ray irradiation on these materials, which you'll see more details here in a bit. And we were able to push this up even further. So by shooting this with gamma rays, we're able to improve both the modulus and the strength. All right. Now, there's some other things going on this graph. Those requirements I showed you a few slides ago from NASA, that's this mark right here. That is actually quasi-isotropic properties. What we found early on is that we really needed to perfect unidirectional composites. Once we perfected that, then we can go back and work on quasi-isotropic, which is what we're doing now. Those results I'm not going to present to you because that's still in process. But what we're going to focus on today are these unidirectional properties that have taken us well beyond state of the art. All right, now what I'm going to do is I'm going to go through 4 more detailed explanations of some of the projects we're working on. What I'm going to do first is talk about 2 of the experimental-based ones, so you get an idea of how we made this material. Then I'm going to talk about 2 computational projects that helped inform these experimental projects to make this computationally driven materials research. I'll show how the computation provided clues and little pieces of information and understanding that were vital for us, not only to design these materials, but understand their behavior. So let's talk a little bit about carbon nanotube yarns. I'm going to assume for a moment that most of this audience is familiar with carbon nanotubes. If not, I can briefly explain. They're small tubes of aromatic carbon that, if they're structurally perfect, they provide the highest stiffness and strength unidirectionally that's known to man, essentially. All right. The trick over the years, though, is that we've been working with carbon nanotubes pretty consistently as a research community for the past 2 decades. Really, for the first 15 years, not making a whole lot of progress because these carbon nanotubes tend to be so small, they're really hard to grab in a composite. For composites people, you know that what makes composites work are the carbon fibers or the glass fibers. The matrix, essentially, we can transfer load between the matrix and the fiber, take advantage of those properties of the fiber. But when carbon nanotubes, they're so small, sometimes it's hard to get that load transfer. All right, so then the next major intuitive jump would be, let's take carbon nanotubes, let's put them together and make a tow or a yarn or a fiber. All right, and so that's what you see on the left. That's a carbon nanotube yarn. It's kind of an odd, funky shape, right? So these carbon nanotube yarns, this one is manufactured by Nanocomp, as of all the materials that we use in this research, are these carbon nanotube materials. So the carbon nanotube yarns, they're not necessarily round. In fact, as you'll see, we don't necessarily want them to be round. They can come out in different shapes depending on the processing. There's a whole range of different types of processing that can be used. And so based on that, they come out with different forms, and we can use that to our advantage. So on the left, you see a cross section. That's a SEM image of it. You can see the scale bar there. But in that image on the right, the large image there, that's a TEM image. You can see the scale bar. We're on the nanometer length scale. So in this image, we're actually looking at individual carbon nanotubes. Now, you see in here some of these large circles right here. All right, those are actually large multi-walled carbon nanotubes. And what you could also see in between them are these little layers right here. These layers were at one time open carbon nanotubes, but they collapsed. So they basically self-assembled in between the open carbon nanotubes to form a highly dense load transferring material. So if you think about it, a carbon nanotube is great. It's very stiff and strong, but there's a lot of empty space in the middle, which helps to reduce its mass, but that space does not help us in transferring load at all. If you think about what happens if we can collapse those and make planes, little aromatic planes right here that are all connected, you can see how we can now start to transfer a tremendous amount of load with carbon. And carbon is very lightweight, so we can transfer the load. We're still not dealing with iron or aluminum or titanium metals. We are still dealing with carbon-based materials that are very lightweight. And so in these materials, we see this is the type of molecular structure we see. There's some other things in here. These are the residual catalysts. So in order to make these materials, we have to have metal catalysts involved in the process. And those typically are still in material when they come out of the manufacturing. There's not a whole lot we can do about that. We have played with that quite a bit. There are things we could do, but it's hard to get rid of that completely. But the main thing is you get an idea here that inside here, there's different forms of carbon nanotubes. And put together, this forms a carbon nanotube yarn, which has some pretty remarkable properties compared to carbon fiber, not only in terms of stiffness and strength, but one of the major advantages of this type of microstructure is the flexibility of the yarns. Whereas carbon fibers, if you bend them too much, they will snap. They're brittle enough to do that. These carbon nanotube yarns, they don't like to snap. When you bend them, they like to just bend. So we can make all kinds of really interesting woven patterns or preformed patterns using carbon nanotube yarns, which is a big advantage. All right, so the FSU team, Cecil and his colleagues, what they did, they made some composite panels out of these. So you can see on the upper left here, these are the panels. If you take a look here at a cross section of these panels, this is one of these panels. It's embedded in epoxy. So what you're seeing at the top and bottom here, that's just the epoxy it's embedded in. That's not part of the composite panel itself. If you take a look on here, and then you see this magnification of what's going on, you see these little individual regions outlined in red. Those are carbon nanotube yarns. And I told you earlier, they're not only flexible in terms of bending the yarns, but they're flexible as far as their cross section goes. And with carbon fibers, you're pretty much stuck and pack those so tightly. But with the carbon nanotube yarn, with its flexibility, you can pack it even tighter. You can even take up a lot of these little spaces. You can see the resin-rich areas are tremendously reduced when you're using a carbon nanotube type of morphology in these composites. So if we still have resin in between them for the load transfer, but we get rid of the resin-rich regions, which means we can drive up the volume fraction and drive up the material properties, including stiffness, strength, and toughness. So this material, and again, the citation was a couple slides ago. I encourage you to look at that paper if you want to see more details. But in that paper, we also outline the process of testing these laminates. This work was done at the University of Utah. You can see some of the images here. You can see that when they're tested, they do fail in tension. The yarns do break. It's not like they slipped out of the grips. They're very good at what they do there. They were able to get the failure to occur the right way. And you can see the failure mode. And this graph is very similar to what I showed a few minutes ago, but this is specific to the paper for the results of this paper. And what you can see here is the standard deviation of the different laminates that were fabricated as part of this individual effort and where they stand on this property graph. By the way, each of these data points represents a different matrix resin. So I believe this top one was a benzoxazine. We've got a bismaleimide. We've got some cyanide esters in there. There's more details in the paper. But by being able to use these types of carbon nanotube yarns, different resins, we're able to show very nicely that this type of composite works really well for dramatically increasing the modulus over state-of-the-art composites. All right, now I had hinted earlier what we did next. So this paper that just recently came out in Carbon, we actually took these composite materials, we irradiated them with gamma rays. So straight out of Marvel Comics, we shoot these things full of gamma rays to hope to make them stronger. And so what you could see right here is a typical side view of a carbon nanotube yarn. And what you see here is a combination of SCM and TEM images. Now, what you get out of this comparison, so the left-hand side is before irradiation, the right-hand side is after irradiation. And what's interesting here, if you're looking closely, trying to figure out the differences, you're not going to see them. And that's the whole point of this figure, is that the gamma rays do go in, they do their job, but they don't completely destroy the material, as you may be afraid they would do. In fact, their effect is somewhat subtle. We can get it on other characterization techniques. We can see that it actually forms little molecular crosslinks between the carbon nanotubes themselves, or crosslinks between the carbon nanotubes and little pockets of amorphous carbon that are also present right here. All right, and so by doing that, the idea is we can increase the strength. So here are the results of that work. We'll take a look at the left-hand side first. This graph shows the specific strength of these composites and the specific modulus as a function of the gamma ray dosage in kilograms. So the green is the specific strength. You can see the baseline here is no irradiation. And we start to irradiate it a little bit with a 200 dose and a 700 dose. We're able to push up the strength and the specific modulus up to this maximum level. Now, if you get a little bit too crazy with those gamma rays, it starts to slowly degrade the material a little bit, which of course is not desirable. So there's a nice little sweet spot there. Now, the nice thing about our institute is we can go in the lab and we can get these results. And, we could just publish a paper on this just as it is. But it's also really nice to be able to look at the details, try and get a physical understanding of what's going on. And so with our molecular modeling folks in the institute, and I'll show you some more examples of this, we're able to go in and take a look at what's actually going on, maybe come up with some models to try and replicate what we're seeing, just so we can understand what's happening. So Traian Dumitric at the University of Minnesota and his team developed this multi-scale model, molecular model on the top, a mesoscale model on the bottom, where the idea is we actually look at the defects. So when a gamma ray comes in, knocks out some carbon atoms, it also creates bonds that weren't there before that are now formed. These are the crosslinks. And so we could take a look at the different types of vacancies that we create, and we could get a good idea of how these bonds form. Also, we could take a look at how these crosslinks you see in purple, how they affect a carbon nanotube bundle. So it's not just, what happens between two parallel sheets, but what happens with the bundle in the lower. In computational simulation, looking at modulus, we can show that there is indeed a sweet spot where if you create the right number of crosslinks, you can maximize the modulus. If you make too many crosslinks, you start to degrade the material. All right, now two more things I want to go over. These are more modeling-based projects that help augment some of the things you've already seen. Now, one thing I want to make really clear before I talk about this is that within the Institute, there are all kinds of projects. We have lots of publications, lots of individual things that we looked at, lots of great works by a lot of great people. Of course, there's no way I could go through all of that in this presentation today. So I only had to pick one little thread of projects that kind of go well together in order to present. And so this paper that was first authored by Prashik Gaikwad, this is essentially molecular dynamics modeling, trying to understand what's physically happening when these materials, when we have amorphous carbon, we have the carbon nanotubes, and we're shooting it with gamma rays. So whereas on the previous graph I showed you, that was more individual nanotubes, nanotube bundles. This was focused on what happens at the interface of amorphous carbon and nanotubes, because there's a lot of amorphous carbon in these carbon nanotube yarns. So on the left here, what you see is a diagram of the molecular dynamics model. Not only we're looking at creating crosslinks between the carbon nanotubes and the amorphous carbon. In this model here, there's actually two parallel aromatic planes right here. That's to model the flattened carbon nanotube. All right, our MD models can't be really big, so we only can do a little section of it here. But we played around with putting crosslinks between the amorphous carbon and the carbon nanotubes. All right. We also took a look at what happens, even if we cross-link inside these flattened carbon nanotubes so that we get the load transferring from one side to the other. So we're taking a look at both scenarios right there in the molecular dynamics model. So what we see here as the result is the graph on the right. So this is a true stress versus true strain plot. We'll talk about each of these series individually. You see we have a couple of this orange, blue, and the gray. This is what happens when we have no crosslinks. We do get a stress-strain response. It's maybe not as good as we would like. But now, if you take a look at this black line, what happens if we now put crosslinks between the amorphous carbon and the carbon nanotubes? We see that we can increase the strength, so that is the black versus the gray line here. We can increase the strength quite a bit. A little bit more dramatically, we can increase the toughness. So the total area under this curve grows quite a bit. Now, what we did see, though, is that even if we put that crosslink in there, there's still no load transferring from one side of the nanotubes to the other. So then we put little crosslinks in between the carbon nanotubes, and we get this green line, which now that tells us that we can dramatically increase the toughness of these materials if we can control where these crosslinks go. Now, this is a modeling paper. This is not to say that we could go in and strategically put crosslinks in an actual material. But what it does tell us is that if we could, we know exactly where these crosslinks need to go, and we know how many of those crosslinks need to be put in. So this is a good example of not only being able to drive the direction of research, but also give some sort of physical explanation of what's happening in what we observe experimentally. Now, the final thing I'm going to go over here is another modeling paper that goes along with this out of Tryon Dimitrica's group at the University of Minnesota. And that is the idea we can use computational simulation to look at the packing of carbon nanotubes and how that affects the carbon nanotube yarn behavior. You can imagine this type of information would be really useful to a company like Nanocomp, who Nanocomp can control all the manufacturing parameters of these yarns. And so with information like this, they can get an idea of how to adjust their parameters in order to yield the best carbon nanotube yarn material that they can. So by using some basic TMCT imaging, some really interesting analyses where we can go in, we can isolate where the carbon nanotubes are. We can take a look at their diameter, their eccentricity, how they're modeled. We can actually do a really good job of understanding what the topology is. Once we have an understanding of the topology, we can build models and we can run them. So these are molecular scale models where we start with just a square packing. We start to go through a simulated processing of these yarns. We let the carbon nanotubes do what the carbon nanotubes want to do based upon their molecular and atomic interactions. For example, a model like this would tell us that two carbon nanotubes beside each other, when they do flatten, they'll flatten very nicely in this array. However, if their diameters mismatch, then we don't get quite the type of efficient packing that we want. And by controlling the diameter of the nanotubes, controlling the distribution of diameters of the nanotubes, and controlling the pressure involved in manufacturing, which Nanocomp can control, we can actually look at how these yarn geometries form, how the morphology of the carbon nanotubes form, and how we can control that. And if we know this, we also know their predictive properties. And so this is a really good way that we can use computational modeling to help adjust processing parameters to help drive the material development. All right, so I'm going to go through some acknowledgments, and then we'll have some time for Q&A. So first of all, I want to thank the NASA Space Technology Mission Directorate for the opportunity to do this research. Claudia was our program manager, as well as Matt Deans, also our program manager. I want to thank that group for the funding, the support, the tremendous amount of support. You know, NASA really wanted to see these space technology research institutes succeed, and they are succeeding. And because of that, they were great to us, and they continue to be great to us. Like I said, the OSComp team is massive. If you look at all the researchers, students, the administrative staff, everybody involved, all the people in the companies, there's no way I can list them all here, but all of these people together helped achieve all the things I showed you today. For me personally, I also want to thank my current research team, Sagar Swampnil, Ivan, Josh, Kate, Trevor, Tristan, but also all of my former team members. There's too many of them to list. I saw some of them are here. I want to thank all of them. All of their work helped lead us here. My NASA colleagues who are really highly involved this whole time, Mia, Chris, and Ben. There was other folks at NASA as well, but those three really played a really critical role in everything that we're doing here. Our AFL colleagues, their support along the way. Me personally, I want to thank my career mentors, Machi Kamosa, my PhD advisor, Tom Gates, my first postdoc advisor, Bill Predabon, my longtime department chair who just recently passed away, Mia, who's been there my whole career, actually. I consider her very much a mentor, and Byron Pipes, who many of you know, he goes back a long way. So with that, I want to end this presentation, and I'd love to have some questions. So Martin says, interlaminar tensile and shear strength are often the limiter for composite applications. What improvements are foreseen in interlaminar tensile? I think it means interlaminar tensile and interlaminar shear strength. So, very good question. The interlaminar region has always been a problem. One of the projects we had on here, and actually I was thinking about this morning, I wish I would have had time to include it. Part of what we were doing at USComp is we had Brian Wardle's group. I don't know if you're familiar with a lot of the research they're doing. They were a very important part. And one of the things that they do is that they like to take a look at composite laminates, but in that little interlaminar region, they do a really good job of putting different types of load transfer materials in there, whether they be carbon nanotubes that are oriented sort of in a forest pattern or however that is. With that, shear strength actually increases quite a bit. So much, if you take a look at those results, it mitigates crack movement in the interlaminar region, forces the crack to go into the intralaminar region. And so that's one of the things we've looked at in order to try and increase that interlaminar shear strength. Current fabrication limitations will prevent any one carbon-carbon section from exceeding approximately 5 meters in its largest dimension. Large carbon-carbon sections, therefore, must be manufactured in the form of tiles instead of a single piece, resulting in numerous seams along the windward side of the vehicle. These tiles aren't exactly the best solution for emissions. Can this 5-meter limitation be overcome? Before we can use our materials to do that, we have to actually scale up ourselves. So we're at the point now where we can make a little panel, right? A little 4-inch by 4-inch panel. We can test those. These carbon nanotube yarns are still pretty expensive to make. They're pretty time consuming. A lot of resources have to go sort of more focused on creating something on the panel level. Now, yeah, you're absolutely right. If this is to go as a technology insertion at some point, we're definitely going to need to exceed that 5-meter barrier. And I'm hoping some of our colleagues in the composites community, as we develop this technology, will be able to address making larger scale structures. We are, by the way, making a component. However, we're not really ready to share too much of that information yet. But we have a TRL level 5 objective that we're planning to achieve by the end of this year, by the end of this, by summer of 2024, I should say. The next question, one of the common hindrances I've run into for using composites in the aerospace industry is the lack of qualification data. Is there work being done to give credence to the use of computational modeling to provide some of the qualification evidence? Yeah, that this is us computational people. This is something we should never, ever forget, that yes, we can come up with all kinds of great models, all kinds of great predictions, but is it right? Is it useful? Is it validated? Yes, that is always a common theme with us. And so the idea is a lot of the models, to the extent that we can, we try to validate everything as much as we can. Now, when you're designing materials for the future, you can't always make the things that you're modeling, unfortunately. So sometimes you have to take some liberties in the modeling. But for the most part, we try and validate where we can along the way. All right. Great talk. How do you model gamma ray in MD simulation? We did not actually model the gamma rays themselves. We actually modeled the corresponding damage that gamma rays would cause. We were able to go into the literature and learn a little bit about the effect of gamma ray radiation on an aromatic carbon plane, and we were able to put that into the models. So there is some work out there. I know about halfway through our project, there's some folks at Penn State who can, I think, model the actual irradiation, but that was a little bit beyond the scope of what we wanted to do. Okay, using the carbon nanotube, how do we incorporate boundary conditions at the interface, especially in the modeling process? Well, the good thing is when it comes to the boundary, so the CNT where it meets whatever it's next to, whether it's another CNT, whether it's amorphous carbon, or whether it's a polymer, the nice thing about the modeling process, we have complete control over that. We can model what's happening at the interface. We can model chemical crosslinks that occur at the interface. If there's no chemical crosslinks, we can at least model the charge transfer, the van der Waals forces, the corresponding change in the molecular structure that occurs there. So all that's incorporated into our molecular models. Has the gamma ray radiation research provided any insight into the potential useful life of the composites in the radiation environments experienced in the space outside of the Van Allen belt? Really good question. Actually, when we first put the proposal together, we were so excited and stoked. We were going to solve all the world's problems. We were going to develop this material and we were going to test it in these conditions. We were going to design this material to withstand cosmic radiation and all that stuff. And the NASA folks were very wise, and they got our proposal and they said, this is great, but there's no way you can do all this stuff. Why don't you just focus on the mechanical properties? And they were right, of course. Instead of focusing on that, we focused only on the mechanical properties, because that in itself was a major obstacle. So what we're hoping is that with this material, the next step for the materials community would to be look at things like cosmic radiation and ultraviolet radiation and how that affects these materials. What is the permeability of these CNT yarns like? Do they suffer from issues such as dry spots due to their densely packed structure? Brilliant question. Yes, they are not very permeable to resin, I think is really what that question is asking. When you're making a composite, does the resin like to infiltrate the carbon nanotube yarns? Resin doesn't really infiltrate carbon fibers very well, and it does not necessarily, permeate into the carbon nanotube yarns very well either. But keep in mind, though, the technology for carbon nanotube yarns is very young. We're still playing around with trying to change that. So preliminarily, the answer is they're not very permeable, but I'm convinced, as NanoComp develops their processes, as we develop new processes for making composites, we can change that. All right. Next question. Do you see coarse-grained models playing an important role in using simulations to study advanced composites? I imagine it doesn't make sense to create coarse models of structures like carbon nanotubes alone, but what about for the polymers in the matrix material? Yeah, really good question. Yeah, absolutely. So in this project, we had atomistic models like DFT models. We had molecular dynamics models, and we also had continuum level models. But right there in the middle, we had our mesoscale models, which are, that's kind of a broad term that includes things like coarse grain models and other similar things like that. So yes, absolutely. Composites are a multi-scale structure. Molecular modelers like me, we do not give you all the information you need to know. We're only giving you information of what's happening on the molecular level. You really need a multi-scale effort if you want to model composite materials, including coarse grain. When you get to large sections where you've got, you want to model, maybe thousands of polymer molecules, not atoms, but molecules. So yeah, coarse grain is important. For those of you developing coarse grain models, please keep doing it. It's very important.
Thank you, Professor Odegard. Thank you for our audience. We wish you all a happy holiday season, a happy new year, and look forward to joining with all of you again